Hello everyone and welcome to another video. So I'm very excited for the discussion today because we are going to be introducing a concept that is very near and dear to my heart, and that's the concept of mathematical optimization. At a very basic level, mathematical optimization is all about trying to pick a quote-unquote best element from a set of available choices. Now, while this might sound exceedingly simple, we're going to see that this is one of the most studied and contemplated mathematical concepts in human history. The reason it's so deeply studied is that if you look at things long enough, almost every science and engineering problem, and actually every life problem in general for that matter, really can be framed as an optimization problem. Now, I know it's supposed to be a mathematical discussion today, but if you pardon the pun and let us go on a small tangent, get it? We're going to see that if we put our philosopher's hat on, we're going to see that optimization, it's really a reflection of the human experience. Now, I know that sounds really deep and all, but really, aren't we all just trying to do the best that we can with what we've got? So to motivate that, let's go and take a look at a very simple example. All right, so we were just talking about how optimization is basically the story of human existence. I've got a demonstration set up here to see if it's also the story of canine existence as well. So for those of you who've been watching the channel, you know that this is our dog Gus, and he helps us with visualizations and demonstrations of engineering and scientific principles. So let's see if he can help us understand optimization from a very high level. As you know, for those of you who probably have dogs, you know dogs are extremely food fixated, especially for Gus. I think he spends 80% of his day just thinking about what he's going to eat and how he's going to get something better to eat. So from his perspective, optimization of his life basically revolves around what can I eat. So my daughters have helped me out a little bit. They've made some signs where we can put 3 different foods for him that are either close, a little bit further away, and much further away. So on this side we have dog food. Gussie, do you like dog food? Stay. This is his dog food. I mean, he eats it. I don't think he loves it. And then over here in the middle, we have Fruit Loops. Gussie, do you like Fruit Loops? Okay, stay. We just discovered he likes Fruit Loops this morning when he was harassing my daughter and basically stealing all of her Fruit Loops at breakfast. And then on the far side, we have pizza, which I know he likes. You like it? No, stay. Wait, Gussie. So over here is pizza. Right? So like we said, optimization is about trying to do the best thing that you can within a given set of constraints. So let's see, is he going to spend the extra time walking over to the pizza, or is he just going to go for his dog food because it's close and within reach? You ready, Gussie? You want to do something? Okay, ready? Run your optimization algorithm now. Go! Aha! See, so his optimization routine in his brain decided that the pizza was the best thing to do, even though it took him longer to get to the food. And now let's see if he's going to actually eat. Are you going to eat the Fruit Loops? Gussie, okay, you can eat whatever you want. Okay, Gussie. Gussie, do you want the Fruit Loops? Gussie, look! These live demos never seem to. Okay, now he decides. His nose doesn't work so well any longer. I think so. He might not have smelled it, but apparently now he's going to spend some time eating the Fruit Loops. And I know we let this run long enough. He's actually going to completely ignore his dog food. He really doesn't seem to like that, right? So this is one example of optimization. Let's see if we can change the picture ever so slightly. For example, what if we were to bring him back and reset him? Okay, Gussie, hold on a second. Can you stop eating Fruit Loops for a second? Okay, stop. Okay, come over here. Gussie. Let's reset. Okay, sit, stay. Okay, now, what if let's reset the picture. Let's go ahead and add some more Fruit Loops for him over here. We'll make this nice and clean. Okay, and let's put more pizza over there for him. Just like we had last time. Gussie loves pizza. Stay. Okay, here's pizza. Okay, so it's almost the same setup, but now let's put some constraints on him. I'm going to tie him to this table with his leash, and now it's almost the same problem, although, again, the question is, what's the best thing he can do given his set of constraints or given what he's got to work with? So let's see what happens now. Ready, Gussie? Okay. Oh, he can't get the pizza now, right? So let's see, what is he going to do? Does he decide to now, okay, Gussie, keep going. Aha! Isn't this interesting? Now, under this set of constraints, his optimal solution to the problem, or what he decides to do, is a little bit different. He decides, okay, well, I can't get the pizza, I'm just going to eat the Fruit Loops. Okay, Gussie, you can eat. Oh, no, see, he's not, he's still going to go for the pizza. Okay, again, I apologize. I know live demonstrations with dogs sometimes don't work as well, but hopefully this gives you an idea of what optimization is at a very high perspective, right? Again, the constant refrain and the constant theme is basically, again, trying to do the best you can with what you've got. All right, so as we saw from the example, optimization, the whole goal of mathematical optimization, we really can write this down in one sentence. All you're trying to do is you're trying to optimize some function. Let's call that function f, okay? Now, what do we mean by optimize? What that usually means is you're trying to make that function as big as possible. So you either want to maximize f, or you want to do its converse. You want to minimize it. You want to make it as small as possible, right? So in this case, like if this function here is measuring something like, say, the number of cars that are produced in a factory in a given month, right? You would probably want to make that as big as possible, right? So you would want to make this number as large as possible, so you're trying to maximize f, right? So in this case, this f is typically referred to as a utility or an objective function, right? Because you're trying to get the highest objective value or the most utility out of this factory, right? And again, that's what this function f is supposed to measure. It's supposed to measure, again, the number of cars produced per month in this factory. You want that as large as possible, right? So the other way you could look at a lot of optimization problems is you might want to minimize f. So what if this f was something else, like this function measured the production costs associated with a single car, right, coming out of this factory? Well, you probably want to keep production costs as low as possible, so you want to minimize this f function. So in the cases where you want to minimize this f is typically referred to as a cost function. And again, this is really just nomenclature. All these functions are, they're just scalar functions where we're going to see multiple things come out, and all that comes out of this function is a single scalar, which tells you either the utility or the cost associated with a given action, right? So again, from a high level perspective, it's really simple. This is really the goal. You just want to either maximize or minimize f, right? Now, while we're talking about notation, one other thing that I'll maybe mention that you may see in a lot of text is that a lot of text will use the value j to be the function value at a specific location x, okay? So j, this is typically your objective or your cost function value, right, at a given x, right? And we're going to talk about what is this x. Actually, you know what? Maybe we should talk about that exactly right now. What is this x, right? So a lot of these problems, the objective function or the cost function, right, this function f, it is usually dependent on several different variables. So let's call these maybe, you know, you might have an x1, an x2, all the way up to xn. There might be these variables which influence the cost, or they influence the value of this function f, right? So these are sometimes referred to as control or decision variables, because these are the variables that we are going to be tuning or changing or controlling or making decisions about in order to try to influence the objective or cost function value. So the picture that goes along with this now is, mathematically, you have all of these inputs. So you have an x1, you have an x2, you have all the way down to xn. There are all these things which influence this objective or cost function, right? So j is equal to f of x1, x2, xn, right? And out of this comes this value j, which is just the function evaluated at those locations, x1, x2, all the way to xn. Right? Something like that, right? So this is the overall picture where this here, again, is either the objective or the cost function, depending on if you're trying to maximize or minimize the problem, right? So let's look at a couple of examples. So how about example 1? How about, you know, aircraft endurance, like how long an aircraft can stay in the air. Right? For those of you who know, I'm an aerospace engineer, so I'm very focused on aircraft examples. So what influences how long an aircraft can stay in the air? Well, I don't know. One thing is how much fuel you have, right? So fuel supply, maybe measured in gallons, right? That's one thing that definitely influences, right? You carry more fuel, you can probably stay in the air longer, right? How about X2? Another thing, how about the drag coefficient of the aircraft, right? That probably has something to do with its endurance. Let's just keep going. X3, what else might influence it? How about air density? Right, that probably has something to do with it. Let's just make one more just for giggles. X4, how about the total aircraft weight, right? That includes, you know, passengers, structure, fuel, all that kind of good stuff. Depending on, you know, you have a larger or smaller number here, that probably influences the aircraft endurance. So again, you can think about this picture where this cost function or objective function F, you basically tell it how much fuel, what the drag coefficient is, the air density, how much the total aircraft weighs, and in this model of our system, this would be able to tell us how long can the aircraft stay in the air, right? So that's what this value J is for a given set of these 4 variables. Maybe you have 100 gallons of fuel, you have a drag coefficient of 0.02, you have an air density of 1.225 kilograms per meter cube, you have a total aircraft weight of, you know, 50,000 pounds. All that stuff will tell you, the cost function will tell you how long you can stay in the air. Right? Let's look at another example. What's another example? Oh, shucks, I kind of ran out of some space. Maybe, let me erase this real quick, okay? Let's look at another example. How about example 2? How about the cost, how much money it costs me to commute to work? Right? This might be a function of multiple variables again, right? Something that influences how expensive it is for me to commute to work is, how about the distance to commute? Like how far away do I live from my work location? Another variable that might matter is what method of transportation do I choose? You know, do I take the public transportation, or do I ride my bike, or I drive, whatever? How about something else? X3, maybe current fuel prices influence this, right? And again, you can see, you can start tacking on as many different decision variables as you want, depending on how much fidelity do you want this objective or cost function to capture, right? So again, within the context of maybe discussing nomenclature, if you think about this in example 1, right, typically with the aircraft endurance, you want to stay in the air as long as possible, right? So in this case, I would probably call this an objective function, right? And the goal of my optimization problem is to maximize F, right? Because I want to stay in the air as long as possible. It's exactly the opposite here with example number 2, where this function here, F, is computing how much money am I going to have to pay in order to commute to work. So I'm a cheapskate. I want to keep that as small as possible. So example 2 is a very similar problem, except now instead of maximizing F, I want to minimize F. So F, in this case, might be considered a cost function instead of a utility or an objective function, right? Okay, and while we're talking about maximizing F or minimizing F, I thought we would interject very briefly, and I wanted to point out that actually, if you think about this long enough, those two are actually very similar, almost equivalent problems, right? Just conceptually, let's look at a very simple case, right? If you were trying to look at, say, this situation where you have an objective function F, right? So you've got, let's consider a very simple system where it only has one independent variable. Let's just call it x1, right? So this objective function f of x1, right? This is the objective function value. And let's say that this function looks, I don't know, something like something like this, right? So obviously, it's a very simple problem here where you're just trying to find the maximum value of it, and you can see that occurs right here. So this is like your optimal choice, right? Because that's what you're trying to do. You're trying to find this x star value, which maximizes the cost, maximizes the objective function, right? So here, this is our objective function. Right? Well, what's interesting about this is for a lot of optimization problems, we like to talk about minimization of the function instead of maximization of the function. And really, the two of them are just related through a multiplication of a -1, right? You can basically go between these two functions by just multiplying by -1, right? Because if you multiply this objective function by -1, right, what does it do? It basically looks like the mirror image of it, right? It looks something, I'm gonna try to, oh boy, okay, something like that, right? This is what happens if you take this top thing and you multiply by -1, right? You get this thing down here, which is another function, which now you can consider to be the cost function. Right? And now, if you try to minimize this function, right, you see the minimum occurs exactly at the same spot, right? So these two problems are, again, just duals of one another. They are basically the same problem, just there's a -1 multiplication of the objective function to get to the cost function, and vice versa, to get from the cost function to the objective function. So in a lot of optimization texts and a lot of applications, you're going to see we're mostly going to talk about minimizing a cost function, right? But just in the interest of keeping things general, I wanted to point this out and say that, you know, for the rest of this discussion, you know, we might be talking about maximizing an objective function or minimizing a cost function, but further on down the road, as you start digging deeper and deeper into optimization, you're going to see textbooks start to ignore objective functions and just talk about cost functions, because as we see here, they're exactly the same thing, right? It's very easy to go between a maximization problem to a minimization problem. It's just a multiplication of a -1. So while we're staring at this, you know, one other thing to think about is that we talked about all these x's that we talked about, right? These x's, these are what we're calling controller decision variables. We're basically saying you are able to pick different combinations or permutations of x1, x2, x3, x4, etc. in order to try to tweak the aircraft endurance or try to minimize the amount of money you spend going to work. Well, one thing that's interesting is that these variable values are not completely free in most engineering applications. You can't arbitrarily choose any value between -infinity to +infinity for each one of these, right? For example, just look at this case right here, the amount of fuel. You can't have negative fuel, right? The minimum number of gallons you can stick in the aircraft is probably 0. So this x1 value, it probably has to vary between 0 and whatever the maximum fuel capacity of the aircraft is. Same thing with drag coefficient. In fact, most of these have to all be positive. I don't think you can ever have, it doesn't make physical sense to have negative values, and some of these have a minimum and a maximum as well, all right? So this is the idea of constraints, right? So actually, tell you what, give me a second to erase some of this board and we'll talk quickly about constraints. All right, so to set the stage for a discussion on constraints, let's look at another example. An example here is, how much does it cost to produce a certain baked good? Slight side note, I don't know about you, but I love me some baked goods. Actually, my daughters have yelled at me multiple times because they've sat there and them and their mom, they've gone ahead and they've baked a tray of cookies, and when they're sleeping, I've been known to eat not the whole thing, but I'll eat a lot of them, and I love going to bakeries. I get donuts, cinnamon rolls, whatever, like, they're great, all right? That being said, I may want to produce these myself, but I want to keep the cost at a minimal, right? Now, the cost that goes into making a cookie or a baked good, maybe there's two key ingredients, ingredient 1 and ingredient 2. Let's call x1 is the amount of ingredient 1 in this certain baked good. x2 is the amount of ingredient number 2. So this could be like salt and sugar or something like that, right? Now, how does this fit into an optimization problem, right? There may be constraints on these two decision variables, right? Because you can't just pick any arbitrary amount of salt and sugar and expect this to work, right? So for example, I've just cooked up and concocted some quasi-fake constraints. You're going to see very quickly that I'm not a very good baker, but at least they seem to make some physical sense. So this is one thing that's very interesting with optimization is you're going to see that with optimization, you are able to incorporate, or again, pardon the pun, bake in a lot of physical, constraints or requirements into mathematical definitions. So for example, the amount of ingredient number one, it can't be negative. So one way to express that mathematically is with an inequality, right? So x1 has got to be greater than or equal to 0. Right? Similarly, I look in the cupboard and maybe I only have 0.75 units of ingredient 1 available. So I can't throw in boatloads of salt into my concoction, right? I'm limited that x1 has to be less than or equal to 0.75. So again, we're seeing that it's very easy in optimization to turn physical requirements into mathematical either equations or inequalities, right? Similarly for x2, right, for the second ingredient, maybe you might have something like x2. It has to be above a certain level. There's a minimum threshold. You have to include a certain amount of ingredient number 2 in your product in order to meet FDA requirements. So again, that manifests itself in a constraint that looks something like this, right? X2 has to be above this minimum level. And similarly, you might only have 2.5 units of ingredient 2 in the cupboard, so X2 has got to be less than this. And again, you can get even more esoteric and complicated with these constraints on your problem. So in this case, we've got this constraint here, which is 2x1 plus x2 has got to be less than 3. So this might be trying to capture something like the ratio of these two ingredients has to stay below a certain threshold, because if you add too much of these two ingredients in a ratio that is not appropriate, maybe the whole thing turns to mush or it explodes or catches on fire or something like that. Again, I don't know, but you can turn it into a mathematical inequality, right? So these are what are known as constraints on your optimization problem. And what's interesting about this is, let's actually plot some of these out, right? So we said I can draw the entire decision space of this problem, right? We said there's two decision variables in this problem. So I'll draw all possible values of x1 on this axis, all possible values of x2 on that axis. And now what these constraints we're going to see are going to do is they're going to introduce certain regions of this decision space which are admissible or inadmissible. So for example, let's look at this first constraint. We see that what that one does is actually, let's go ahead and draw this in red, maybe for red being a constraint. x1 has to be greater than or equal to 0. So where's the line of x1 is equal to 0? That's right here. So there's a line here, right? And it has to be on this side of the line, right? It's got to be greater than 0. So maybe what I'll do is I'll go like this. I'll make hash marks red to be like bad, right? You cannot go over here. Over here, red is inadmissible. Or the proper terminology that you're going to see from an optimization standpoint is this is what's referred to as infeasible, because it violates that constraint, right? So you can think of it as inadmissible, but really this is the nomenclature you're going to see over and over and over is a problem either feasible or infeasible. And that's all talking about with respect to, do you satisfy a constraint or not, right? So in order to satisfy constraint number 1, you got to be over here. Constraint number 2, okay, x1 has got to be less than 0.75. So where's x1 is 0.75? That's right here, right? So there's another bar here. Oh, sorry, I'm horrible at drawing this like that. And again, it's got to be below this line, so the infeasible regions are out here, right? Okay, that's constraint 1, constraint 2. How about let's go on to constraint number 3. x2 has got to be greater than a half. So that is this line right here, right? And then down here is infeasible. Right, and similarly, let's go to constraint number 4. x2's got to be less than 2.5. That's here. And again, it's got to be below this, so this part is infeasible. Right? And then finally we have this fifth constraint, which is this this kind of, it's basically a line, right? Or in higher dimensions, it's a plane or a hyperplane, if you think about this long enough. So let's see, when x1 is 0, x2 is 3. So we have a point up here, and then when x2 is 0, x1 has got to be 1.5. So we got a point right here, like this, and these should be connected with a line. Something like that. And again, in order to satisfy that inequality, you got to be on this half of the line. So all this region up here is inadmissible. Right? So this is actually pretty fascinating, right? These series of constraints, what we're going to see in optimization is that when you start adding these linear inequalities, we'll talk about that later, you start making these kind of regions in space which are feasible or infeasible. So in this particular problem, we're left with this. I'll try to like maybe trace it in green, green being good or feasible, right? So you end up with this region that looks like this, right? So this is what's referred to as your feasible set, right? And really what this means is this is a region in your decision space which you are allowed to choose because anything in these regions will satisfy all of your constraints simultaneously, right? So maybe what we should do is let's write let's talk about the decision variables very quickly and maybe reformulate it. You can see in this case we just have two decision variables, right? An x1 and an x2. But as your problems get more and more complicated, you can have 2, 3, 4, 5, 10, 100, 1,000. A ton of decision variables. So a lot of times it's a little bit more convenient to lump all of these decision variables into just a single vector. So what I mean by that is let's just make a vector. Oh, come on, this pen is dying. Let me switch. Okay, let's make a single decision vector. Let's call it x, which is really all of these decision variables lined together. So it's x1, x2, all the way to xn, right? And this could either be a row vector or it could be a column vector. It really doesn't matter. All you're doing here is we're lining up all of your individual decision variables into a single vector, and now this vector is typically referred to as your decision vector. Right? No surprise there. That seems to make perfectly good sense, right? Okay, so now with this in mind and with our discussion on constraints, what we can see is we can define this feasible set. Let's call this thing Fs, how about? So Fs is your feasible set, and you can see that its mathematical definition is actually pretty simple. So the feasible set is really all possible values of this decision vector x, right? Such that all constraints are satisfied. Right? That's really as simple as it gets, right? So the feasible set Fs is really nothing more than all possible legal choices of x, and legal means you satisfy all of these constraints simultaneously, right? So the beauty with this now is with all of this infrastructure in place, we are in a position to basically pose the entire optimization problem in a very compact sort of mathematical framework. Let me erase this and we'll write it down. So the problem that we're trying to solve now is want to minimize or maximize the objective function or the cost function value j, which is the objective or cost function value at a given x, right? Such that x is in this feasible set that we just described, right? So in a nutshell, this is typically your traditional optimization problem. And sometimes you'll see it written like this with this little scripty p here, which is basically saying this is the optimization problem here, okay? So again, it's a very compact notation that is basically saying all you're trying to do here is pick some x value which is legal or which is in your feasible set. You want to pick this value such that you either minimize or maximize this objective or cost function, right? Depending on, like we said earlier, if your goal is to minimize or maximize it here. Okay, so again, like I said, it's almost mind-numbingly simple when we step back at it. We're going to see that when you start digging into the details of this is where it gets a little bit more complicated, but stating the problem by itself is actually fairly simple, okay? While we've got this up, maybe while we're talking about nomenclature, this is typically classified as a constrained optimization problem. Constrained optimization problem. Okay, so maybe I should write this as, maybe let's put this PC, right? So maybe, so PC is the constrained optimization problem, okay? To make it unconstrained is actually really simple. Unconstrained is basically this exact same thing, except you don't care about satisfying the feasible set, or you can think about the feasible set is the entire decision vector space. So maybe just to make that explicitly clear, let me write it down over here, and you can compare and contrast, and we can see that they are basically the exact same thing, right? You could pose a very similar problem. Let's call this the problem of the unconstrained system, is to minimize or maximize J is equal to f of x, right? And again, let's box this up, because at this point where you now have a unconstrained optimization problem, we can basically see the only way that these two differ is if you care about satisfying constraints or staying within a feasible set, right? Or you don't, right? So this in general is a lot easier to solve than this one. But again, we're going to see there are tips and tricks on how you can kind of translate between these two. But again, we're just trying to get ourselves situated with the general infrastructure and framework and nomenclature associated with optimization here, okay? All right, so let's look at one more example to see how optimization can be applied to everyday life. For this example, let's expand on the situation we discussed earlier that looks at my daily commute. For those who don't know me, I live in the Pacific Northwest. Specifically, I live on Bainbridge Island, which is about 10 miles west of Seattle, Washington. And I work at the University of Washington, which is actually on the other side of this large body of water called Puget Sound. So the problem I'd like to consider now is, how can I commute from my house to my work every single day? Why don't we brainstorm some possible solutions to this problem? Now, luckily for me, the state of Washington operates the largest ferry system in the United States, so one option is I can just drive from my house down to the ferry terminal, put my car on a ferry boat, go across the Sound, and when I get to Seattle, just drive the rest of the way up to the University of Washington. So let's call this solution maybe Z1, where I drive from my house to the ferry, catch the ferry, and then drive to campus. What else could we do? Well, if I don't want to drive, maybe I'll catch a bus from my house to the ferry terminal, walk onto the ferry boat, and then when I get to Seattle, just find some bus that happens to be going to the UW. So here, that's Z2 here, bus, ferry, bus. What about a third solution? Well, if I want to get some exercise, why don't I ride my bicycle to the ferry terminal, and I can actually put my bike on the boat, take it across the water, and then when I get to Seattle, ride the rest of the way up to the University of Washington. Great. So Z3, bike, ferry, bike. Why don't we think outside the box a little bit? I could maybe now run from my house to the nearest shoreline of Bainbridge Island, hop in the water and swim 5 miles across the Sound here, and then Forrest Gump it to campus and arrive more tired than that creepy dwarf in Snow White. But you know what? Z4, where I run, swim, run, is actually a feasible solution. All right. Let's just skip all of this hoo-ha, and I'm just going to charter a helicopter to take me directly from my house and drop me off at my desk at the University of Washington every day. So, Z5 is just charter a helicopter. You know what? This sounds good, so why don't we stop here? Let's consider these 5 choices to be the entire feasible set for this particular optimization problem. why don't we jump back to the board and think about how to generate a few different cost functions for a few different scenarios within this framework. All right, so we said these were the 5 different possible feasible solutions that we want to consider for this problem. So let's go ahead and just collect all these in one set, which I think earlier we were calling FS as the feasible set. How about let's use a notation, you know, capital big Z. This is the set of Z1, Z2, Z3, Z4, and Z5, right? We're basically just collecting all of these legal choices or legal alternatives to our problem in as one giant set, right? Now, what's interesting is let's go ahead and ask ourselves, can we pose this problem of the commute in an optimization framework? And furthermore, we're going to see, depending on how we set up that problem, the optimal solution might change, okay? So what I mean by that is let's look at a couple of situations, maybe, or cases. Maybe let's call this situation 1. And in here, what I'm interested in doing is I want to minimize time. Okay, so in situation 1, let's go ahead and cook up a cost function, F1, okay, where again you pass in a possible solution. What this is going to spit out is a cost function value, okay, J1, and what this is this is the time required for action Z, right? So if you put Z1 in here, what this function F1 is going to measure, it's going to tell you how long is it going to take you to execute this action, right? So it will measure how long does it take me to drive, ferry, drive. If I pass in Z1, if I pass in Z2, it'll tell me how long it'll take me to catch the bus, then ride the ferry, then catch the bus, etc., right? So within this framework, I have a cost function, right? I have a feasible set. So we can basically pose this as the optimization problem we talked about earlier, where I want to minimize F1 of Z, right? And it's basically an unconstrained optimization problem in the sense that we are allowed to choose this entire feasible set. So we're going to say, well, I guess you know, you can write this. Sometimes what you'll see is, you know, something like this. Z is in big Z, right? And again, since this is our entire feasible set, you might consider this a quote-unquote unconstrained optimization problem because we don't have additional constraints on which of these Z's are legal or not. We'll get to that down the road, right? Okay, so anyway, in this framework, what we're basically saying is all I care about is minimizing the amount of time, how long my commute takes, right? So since our feasible set is pretty small, you can just exhaustively search through each one of these and ask, okay, how long does Z1 take? How long does Z2? How long does Z3? How long does Z4? How long does Z5 take to commute? And then pick the one which is minimal. So I think everyone is going to see pretty quickly that, that the optimal solution is probably just get a helicopter, right? You'll be at work in 5 minutes flat rather than an hour and a half these other actions are going to take you, right? So in this case, the optimal solution is Z5 is optimal. Right? Okay, that's great. And again, makes perfectly good sense. If all you care about is getting there fast, yeah, the helicopter is the way to go. Okay, let's look at another situation. How about if you are super cheap or poor like me and what you want to do is minimize the amount of money, how about, that you have spent, or the cost, literally how many dollars are you spending on commuting, right? So again, let's cook up another cost function, F2, right, where it is going to return the cost function value, which is basically the amount of money required for this action, right? So this is money required for action Z, right? Okay, so it's the exact same thing. Now the optimization problem has changed ever so slightly because our cost function has changed, right? So now I'm trying to minimize F2 of Z such that Z is within our feasible set. right? Now, in this case, it's the exact same thing. You exhaustively search through all of these options, right? And now suddenly, this helicopter option, which used to be optimal, is now very unattractive. In fact, I think this is probably going to score the worst. This is going to cost a ton of money, where all these other ones are actually pretty menial, right? In fact, in this case, what's probably the cheapest, right? It's probably Z4, right? Where I don't have to spend any money. I just have to risk my life by trying to swim across Puget Sound. But that's not captured in this cost function at all, right? This cost function is only going to myopically look at how much money did you spend executing one of these actions, right? So in this case, what's probably optimal is, right, you solve this problem and it is Z4 is optimal. Right? So again, this is very interesting that depending on how you formulate the optimization problem, right, the answer you get changes, right? Okay, let's go one step further. How about, what if you want to have some mix of time and money, right? So let's call this maybe a trade-off between time and money. Right, so this is our third situation, okay? So, in this case, let's make up a cost function f3 of z, right? And its cost that it returns, it's actually, let's make it a combination of these first two cost functions. So maybe what I'll do is we will make this the sum of f1 of z plus f2 of z, and then let's tack on in front of these some scaling factors of each one of these terms. So in this first one, maybe let's put on a scalar q, and on this one we'll put on a scalar r, okay? So in this case, so let's just be explicit about this. f1 of z is the same as earlier, is same as situation 1, right? So F1, if you remember, it measures the amount of time that's needed, and maybe this is expressed in minutes or something like that, what have you. F2 of z is the same as situation 2, right? So this expresses the amount of money, maybe expressed in the units of dollars. And then what these Q and R, these things are scalar weighting factors, right? Which now allow us to, depending on what values of Q and R you choose, it's going to influence whether the system is going to be likely to choose a minimum time, a minimum money, or maybe somewhere in between, right? Depending on these relative sizes. So for example, right, if you have a Q that is large, large relative to R, right? What does that mean? So if Q is big relative to R, that basically means that F1 is much more important than F2, meaning that time, right, is more important than money, right? So this is basically the situation where if you are rich and you're some executive or some CEO and you really just need to get to work quickly, right? You are basically turning this into a minimum time problem because this term swamps the entire cost function, right? So if Q is large relative to R, you're basically reverting to minimize time, right? And in that case, right, we see that the optimal solution is probably back where we were earlier, right? So in this case, Z5 is optimal, right? Okay, now what if you had the opposite, right? What if you had Q was small relative to R? Right? Well, let's just write it like this, we're all consistent, right? Okay, so now, if Q is small relative to R, it's basically the exact opposite situation where this term dominates, right? So F2, you're gonna wanna make F2 very small so that this overall cost function is small, right? So if that is the case, you basically are reverting to a minimum money situation, right? Which is what we saw earlier, right? So in that case, we saw Z4 is optimal. Again, let me just use our quote marks to repeat everything because I want to show there's only certain things that change, right? Now, what's interesting is where if you have Q and R are of relative similar magnitudes, then you might start trading off between these. So I don't know, let's call these like a medium Q and a medium R, right? In that case, right, now you have this situation where it's a bit of a trade-off between time and money, right? So now you have this trade-off scenario, right? So in this case, if you were to formulate the optimization problem P3, right, is again, it's minimize this trade-off cost function such that Z is in your feasible set, right? Now, if you have a medium Q and a medium R, this is where it gets a little bit interesting, where this helicopter one is probably not going to be minimal because its cost is so high. Similarly, this Z4, this run, swim, run, is probably not going to be optimal either because it's going to take forever to do this, right? So instead, something which is maybe a reasonable trade-off, it might be one of these top three, right? And again, it's not clear which one is going to win because it depends on the weights of Q and R, right? So in this case, it's a little bit ambiguous. We would have to have concrete numbers to actually find a true minimum. But in this case, let's just say Z1, Z2, and Z3 might be optimal, right? Depending on what those weights are, right? Now, all of these situations 1 through 3 are, again, what we might consider quote unquote unconstrained, right? Because we didn't put any restraints on the feasible set, right? Other than that it has to be one of these 5, right? Well, let's again modify the situation a little bit more and see if we can change this to be a constrained problem. So I'm kind of running out of space. I want to keep all this in one location. Let's go ahead. Let me erase this line and see if I can jam all of this onto this side of the board. Okay, so now let's look at situation 4. Let's make this basically the trade-off, but let's add, so we'll say trade-off with constraints. Okay, so actually for me, I don't know about you, but I hate going to the gym. I don't go to the gym. I like to go out and just kind of get my exercise organically. So what I might want to do is, can I do that during my commute and kill 2 birds with 1 stone? Namely, what I mean is, can I impose a constraint that on my commute, I want to get at least 30 minutes of exercise in my commute, during my commute, right? And I want to only consider situations which satisfy meeting that constraint, right? So what I mean by that is, let's go ahead and add a constraint to the problem. So constraint 1, right? So what this is I need, I want to make sure my nomenclature is right. So this constraint 1 is obtain at least 30 minutes of exercise during action, right? Okay. So let's go ahead and make a function like a G1, right? G1 of Z. This is this function G1 is going to return the number of minutes of exercise during action Z, right? Okay, so now what's interesting is, let's go ahead and pose this optimization problem P4 as I am wanting to minimize function F3, right? We're still looking at this trade-off scenario, so we're going to use the exact same cost function we generated up top over there for situation 3, where we're trying to have a reasonable trade-off between time and money, right? So this is all the same, right? But now I also want to add another constraint here, so such that I need G1 of Z to be greater than or equal to 30. Right? So this is basically my no constrained optimization problem, right? Where yeah, I've got a cost function, I've got constraints, and now let's ask ourselves, what's the solution to this problem? Now, the first thing right off the bat we can see is that your feasible set has been modified, right? So we need to look through this solution space here of these 5 potential candidates and ask ourselves which one of these are feasible with respect to this constraint that we've imposed. So let's ask ourselves, okay, Z1, does that get you 30 minutes of exercise? Basically, if you pass in Z1 to this function G1, is that greater than or equal to 30? Well, I'm looking at this thing, I don't see any exercising at all, right? Because you're sitting there driving, you're sitting there on the ferry, and you're sitting there driving. So this is no longer allowable, right? Let me do this in another color maybe, right? This will not satisfy G1, so we can't consider that any longer, right? Same thing here. Okay, yeah, maybe you're walking to the bus stop and whatnot, but really this is not a lot of exercise either. So this is gone, right? Okay, Z3, this is totally legal because, yeah, you're going to get a lot of exercise here. You're going to sit on your bum, then you're going to get a lot of exercise. So this is okay, right? Z4, yeah, this is definitely going to satisfy G1. In fact, this is going to be giant, right? You're going to have a ton of exercise by running, swimming 12 miles, and then running again, right? Okay, and then helicopter. Helicopter is also not allowable any longer because it does not satisfy this constraint, right? So now, if you look at this, you're going to ask yourselves, which one of these is optimal with respect to, now we only have 2 choices. So really the optimization problem just comes down to, yeah, do you want to ride your bike or do you want to run and swim? And what's probably going to happen is, again, for reasonable values of Q and R, right, where we're trading off, this is probably not going to be optimal, right? You're probably not going to pick this because it is going to take so darn long to run, swim, and run that this F2 term is probably going to get very, very large, right? Because it's going to take, you know, hundreds of minutes to do this. So this is probably not going to be optimal. So likely what's going to end up happening is this is going to be the optimal solution. So in this case, right, the way we formulated this, now it's Z3 is optimal, right? So again, isn't this fascinating that we had a we were looking at a very simple real world, real life application. We were able to model it using a reasonable feasible set and then just changing the formulation of this exact same optimization problem, right? In situation 1, we had Z5 was optimal. Situation 2, Z4 was optimal. Situation 3, you know, any of these are optimal. Situation 4, Z3 is optimal. But what I'm trying to get at is just by changing constraints, changing your cost function, you can basically influence the behavior of what is optimal. So I guess the other thing that maybe you should take away and we should think about is optimality is subjective, right? A lot of times people say, oh, this is the optimal solution. And a lot of times I think people think, oh, that it must be the unique, I can't ever do any better. It's optimal, right? The word optimal means the best you can be, right? Or the best you can do. But you always have to ask yourself, optimal with respect to what, right? With respect to what cost function, with respect to what constraints, because you see, you tweak some of these just a little bit, you can totally change the definition of optimal. So again, don't just consider optimal solutions to be the be-all, end-all. It's actually the majority of problems in optimization involve, you'll spend most of your time tuning this cost function to be reasonable and tuning your constraints to reflect the mission requirements, right? So again, I just like this example because I think it highlights a lot of these sort of nuances in a very simple, easy to understand fashion. Okay, all right, great. All right, give me a second to erase the board and let's keep on trucking. All right, so as we've seen, optimization is a pretty simple concept where we're just trying to find the minimal of some function, right? Again, this is the unconstrained case, and the picture, right, that goes along with this that I think is probably a good one to draw right now as sort of a summary and takeaway is, you know, let's say you've got some function that looks like, I don't know, like this, right? So here's your decision variables x, here is the cost function value of it, right? And in this case, all you're trying to do in an unconstrained optimization problem is look at every single possible value of your decision variables or decision vector and find the minimal, right? So it's graphically it's really simple. It's just this is what you're looking for, right? This is what's maybe referred to as a global minimum, as opposed to, say, something like back here where this might be sometimes referred to as a local minimum, right? So it's a really simple situation with the optimization problem from a theoretical conceptual perspective, right? It's just find the minimum of the function, right? We saw that this could get more complicated though if you start turning this into constrained problems where you would say add constraints, right? So you might say such that x is within some feasible set, right? So in this case, what if we had a feasible set that maybe looked something like, I don't know, maybe you're only allowed to be within these ranges, right? So this green here is our feasible set, right? So now in a constrained optimization problem, again, the concept is very simple conceptually. It's like within this value of ranges, you're looking for minimums. And again, you see there's still this local minimum here, but now the global minimum of this is actually over here, right? So this is now maybe the global minimum for the constrained problem. So we're going to talk a little bit more about unconstrained versus constrained optimization in the future, but again, I think that I just wanted to draw this picture to show that really optimization from a conceptual perspective is a really simple idea. It's just find the minimum of some function subject to certain constraints, right? So again, this is the summary nutshell. If you want one picture to take away from this discussion where we're trying to introduce the concept of optimization, this is the concept of optimization, right? It's just find the minimum of some function. All right, so from a technical perspective, I think that's what we want to cover today in our introduction to optimization video. This is going to open the door to a bunch of future discussions where we're going to talk about optimization from a mathematical perspective. So we'll talk about unconstrained optimization, constrained optimization, convex optimization, numerical algorithms for optimization. And once we've laid some of that mathematical framework of optimization, we're going to see that this opens the door to an entire world of how to apply optimization to practical engineering problems. So we're going to look at things like how to trim an aircraft, how to numerically solve for trim points in equations of motion. It's a very active area of research. You can use optimization to do path planning. In fact, here's an example of a video of some work that we did previously looking at using optimization frameworks to control swarms of vehicles engaged in a search mission. So again, optimization is the framework for a lot of advanced engineering topics. So I'm glad we had this discussion today where we could at least lay the framework and get some of the nomenclature out of the way so we can start down this journey of studying optimization and I guess following, like we said at the beginning of the video, the rest of humanity and focusing on how to study optimization because it's just so darn useful. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. It really does help me continue making these videos. Another way you can support the channel is via Patreon, and again, I want to take a quick moment to thank some of our recent Patreon supporters. The nice thing about the Patreon support method is that 100% of the proceeds that the channel receives via Patreon are going to be directed towards K through 12 science and engineering for kids and young adults. So, oh, and speaking of the new videos, remember, they come out every Monday, so I hope I'll be able to catch you at one of these future discussions and we can all learn something new together. So, until then, I think I'll sign off. Talk to you later. Bye.